Good evening and welcome to the April meeting of the Nottingham Astronomical Society. This is our very first online live broadcast. Over the coming months we've taken the decision to broadcast all of our lectures live online using the Nottingham Astronomical Society's YouTube channel. Before we start tonight's lecture, just a few details of our forthcoming meetings programme. On Thursday the 16th of April our meeting will be on the subject of the planet Venus. A few members of the Society will be doing short talks on different aspects of the planet. Our meeting on the Thursday the 7th of May will be Jeremy Sears of the British Astronomical Association. Jeremy is the Variable Stars Section Director and also past President of the BAA. His talk will be on an introduction to variable star astronomy. Both these meetings start at 8 PM and will be broadcast live on our YouTube channel. Tonight's meeting we're delighted to welcome Dr. Julian Onions from the University of Nottingham. Julian's talk this evening will be on galaxies, 1 gigayear at a time. If you want to join the meeting, do submit your questions using the YouTube live chat function. Alternatively, you can send your questions to Julian using the Nottingham Astronomical Society's Facebook and Twitter accounts. We do hope you enjoy tonight's lecture.
Well, hello everybody. I hope you can all hear me loud and clear. This is a little new to me, as I'm sure it is to most of you. So just a few things before I start. I'm hoping the technology and internet will hold up throughout this. The interesting thing about doing YouTube live is that it appears about 30 seconds after I say something. So if you quickly type a comment or something like that, it will be about 30 seconds before it sort of synchronizes with me. But anyway, I hope all that's going to work out, and if so, let's get into the talk, and I hope it is all of interest to you. So the title is Galaxies 1 gigayear at a time. It's called Galaxies because that is what we study at Nottingham University. We all study galaxies in the astronomy department there in one form or another. And 1 gigayear is an astronomical term, gigayear being 1 billion years. And that's about the time anything interesting happens to a galaxy. So that's why we've come up with a gigayear, and we kind of throw them around willy-nilly all over the place. You know, a few gigayears here, a few gigayears there. 5 or 6 gigayears ago, that sort of thing. 1 billion years is quite quick to an astronomer working in galaxies. So let's get into what galaxies are. We've got a collection of galaxies here of all shapes and sizes. The ones that we study don't look nearly as beautiful as this for the most part. There's a couple of people who study nearby ones. Most of our work is looking at really distant things, so we don't get to quite appreciate the beauty of them. But another thing to say is that this is a picture taken by the Hubble Space Telescope called the Ultra Deep Field, where it stared at the same patch of sky for 11 days integrated time over about 3 months. And this little patch labelled in yellow is the deepest image we've yet taken, and here it is. And practically everything in that picture is a galaxy. So a bit like turtles, it's galaxies all the way down right to the very edge of the universe. There's more galaxies, in fact, than there are stars in the Milky Way. This is not anything that is anything to do with the talk. It's just keep you occupied. A little bit about distances. So this is the standard distance between the Earth and the Sun, called 1 astronomical unit, 93 million miles or 150 million kilometers, and is so small by the standards we work on, we never consider that. Astronomical units really don't feature. The next one up is the light year or parsec, and most astronomers use parsecs to measure distances, and roughly 1 parsec is about the distance between stars. So the nearest star is about 1.3 parsecs, rounded up to or down to 1 parsec. So a parsec is about the distance between a star. Now, what is a galaxy? It's a big collection of stars, or another way of looking at it is it's a device that will convert gas into stars. So that's what galaxies mostly do, at least during the early part of their life. And this is a picture of our galaxy, the Milky Way, the best picture we can get, because we can't go outside of it. It's far too big for anything like that. We haven't really even explored our own solar system, and that's tiny compared to the galaxy. That yellow disk, get my cursor just here, this is where the sun is, and that yellow ring also encompasses nearly all the stars you can see in the night sky with the naked eye. It's about 100,000 light years across. So 100,000 years for the light going the fastest speed we know to cross from one side to the other. So that's pretty big. It's about 30,000 parsecs, so 30 kiloparsecs. So kiloparsecs is what we use to talk about the size of galaxies. And the next one up, megaparsecs, is the distance between galaxies. So somewhere around a megaparsec is the distance between us and the next galaxy, roughly speaking. It gives you a feel for the scale of things. But, you know, what is a galaxy other than just this big collection of stars? Is the Milky Way all there is to the universe, life, the universe and everything? This was a big question, certainly in the 1930s when some of this was being discovered. And this is a big collection of galaxies that we can see in the night sky called the Perseus cluster. All these fuzzy orange things are galaxies, and there's a few spirals in there. But you can see it's completely embedded in a field of stars. All those white things are stars out there. So the big question was, are these just fuzzy things lying around in our galaxy that we can see, or are they outside the galaxy? Now, it's really, really difficult to measure distances to stars, even our nearest stars. It wasn't really done until the early 1800s, the first distance to a star was measured, and that was one of the nearby ones. Even the furthest stars in the galaxy are very difficult to measure, so it's even harder to try and measure something outside the galaxy, but it was done. Here's another collection of galaxies. This is the Fornax cluster, another group of galaxies, and you can see yet again spread amongst the stars. So can we tell the difference? Are they actually just fuzzy things within our galaxy, of which there are plenty of fuzzy things within our galaxy, or are they further outside, and are they little galaxies of their own, clusters of stars of their own that are very similar to the Milky Way? And it took a breakthrough in technology really to work through this. And this was one of the triumphs of Edwin Hubble and some of the other people at the observatory there. Using the Mount Wilson 100-inch telescope, he managed to measure the distance to the nearest galaxy after a lot of experimentation using some of the very latest techniques of the time. And it wasn't quite correct, but it didn't really matter because it was so far outside the realms of our galaxy that it wasn't really an issue. It was very clear that the nearest galaxy was way, way, way outside the furthest star in our galaxy. So they were indeed separate clusters of stars. And that's what we now know. So, next thing to do, once you're at a new frontier in science, what can you do? What can you try and make of a new science like this? So, as Ernest Rutherford famously said, all science is either physics or stamp collecting. And rather flippant comment that I've often used. But one of the key things of this is if you don't really know what you're doing, one of the things you can do is make collections of things and see if you can see patterns in them, because a lot of science is really discovering patterns and looking at structures. So this is what we mean when we talk about stamp collecting. Can you categorize things together and then go and look for patterns? We've done that in the past, looking at the animal kingdom and indeed plants as well. But you can categorize them into different groups, and you start off by just collecting together similar things, but eventually you start to see patterns in them. You can see things with very common structures, especially if you look at skeletons and things like that. You can see there are connections between, for instance, reptiles and mammals. They share a lot of the same bones and things like that, so you can make connections like that. So based on just collecting stamps, almost, you can sometimes make progress. So can we do the same for galaxies? Here's a collection of galaxies. Is there any commonality that we can see here that would let us group them together? And obviously there is, because that's part of the nature of tonight's talk. And this is a collection of galaxies that Hubble came up with for sort of specifying the different groups of them. And he came up with 4 groups of galaxies. Let's see if I can get my cursor. So this group down here, if you can see the cursor, these are all the spiral galaxies because they look very spiral in structure. They seem to be sort of like water going down a plug hole, that sort of structure, all of spirals. And these are particularly beautiful galaxies that people very much like taking photographs of and putting on their walls, such as the one behind me. These, in contrast, are not nearly so interesting, at least to the artistically minded. These are the elliptical galaxies, and we'll talk a little bit more about those shortly. So these are the very fuzzy type ones. We have another group over here. These are called the lenticular or S0 galaxies, and I'm going to come back to those. I'm not going to describe them now because they're much easier to describe a bit later on. And like any good scientist, you have a bucket left over which you stick in anything that you can't adequately categorize. So over here we have the irregular galaxies down here. So that's our collection of galaxies, and if you can understand that, you're pretty much on your way to being an expert in galaxies. You don't need to know an awful lot more about that. Perhaps, we'll see. So this is the structure Edwin Hubble came up with for his classification. We have the ellipticals along there, E0 to E7, and the number after it tells you how elliptical it is. So E0 is almost perfectly spherical, E7 is quite elongated, much more rugby ball shaped. And then we have 2 categories of spiral galaxies. We have those with bars, which are coming along the bottom, SBs, SBAs, SBB, SBC, and those without bars, SA, SB, SC. And the Milky Way is somewhere around the SBB. So we have a bar in the Milky Way, and the A, B, and C in that relate to how tightly the spiral is wound, whether it's a particularly loose one or tightly wound. So with that defined, we can now go and look at some galaxies and perhaps understand them a bit. So let's start with the nearest one. It's M32 Andromeda Galaxy. This is the one that Hubble measured and worked out how far away it is. It's also a spiral galaxy. It's our nearest neighbour. It's also the furthest object in the universe that you can see with the naked eye, if you're particularly good in a dark sky and know where to look, and your eyes are better than mine, because I have to say I've never really convincingly seen it with the naked eye. You can certainly see it with binoculars or a small telescope. And it's a reasonably large object. Here it is next to the full moon. You can see it's quite large in extent, but this is a little misleading because this is taken with a large telescope with a good camera attached to it. This is really what you'll see if you do manage to see it with the naked eye or even binoculars or a telescope. You see just the very core of the galaxy and just what's at the centre of it. So we're rather spoilt with the Hubble Space Telescope showing us these wonderful images and not really showing us all the detail that we expect to see these days. This is a nice edge-on spiral galaxy, the Sombrero Galaxy. You can see in this one particularly some of the dust produced by stars. That's the black material around the edge. It's sort of carbony stuff, a bit like smoke, but when you get enough of it, it absorbs the light, and we can see some of those. Sometimes edge on, you can see dust lanes in stars. Here's a very nice barred spiral. You can see the bar across the center there, and the two spiral arms moving out from the edge of the spiral, the bar rather. One of the features of this that is particularly clear, which you'll come back to very shortly, is the fact that the spiral arms are particularly blue in colour and the centre is particularly red, or certainly redder than the outside. And this gives us some clue to the science, which I'll come back to very shortly. But firstly, what do they actually look like as sort of physical objects? This is the best description, is a fried egg. So we have a sort of a bulbous bit in the middle and then the yolk spread out. So it looks very much like two fried eggs back to back, is almost a perfect example of what a spiral galaxy looks like. And as for dimensions, it's very similar to a DVD or a compact disc in the width to height, or width to thickness perhaps, of the galaxy. It's a lot thinner than it is wide or broad. And as for the components of the galaxy, this is what we usually talk about. The disk is the very thin part. That's where we live, in the disk, about halfway out. The bulges at the centre, a little more chaotic, where some crazy stuff goes on. And then we have a halo of stars and other things such as globular clusters circling around it, but not nearly as dense as the rest of it. So nearly all the interesting stuff is happening in the disk and the bulge. There's a bit going on in the halo. And you may also have heard of dark matter. So we also have a dark matter halo. This is different to the galactic halo. And this is where the dark matter sits that envelops the galaxy. The galaxy sits within it. And a rule of thumb is it's about 10 times the width of the sort of visible galaxy. So that's a nice quick way of estimating how much of the galaxy there is that you can't see. Going back to other pictures of galaxies, here's one of M81. This taken in different wavelengths to show you some of the contrast. Yet again, another spiral. This is not a spiral galaxy. This is a spiral of galaxy bars. Just a bit of light entertainment. And here's another one. This is one with a lot more arms on it, and sometimes called a flocculent spiral because it's got lots of arms coming off it. Again, very blue on the outside, red on the inside, although this is taken with Chandra and X-ray telescope, so we're overlaid over it, so we're seeing different aspects of it. But going back to the colour, which I talked about earlier, this is what gives us a clue about what's happening in galaxies and gives us our first, perhaps, idea of the science. So a quick diversion onto stellar lifetimes. If we look at our sun, it's a very yellowy or almost white star, and that's because it's burning at about 6,000 degrees centigrade, roughly, or Kelvin on its surface. It doesn't really matter when you get to those temperatures, and by definition it weighs 1 solar mass, because we get tired of writing too many zeros in astronomy. You have to write about 32 zeros after a number if you go to kilograms. So 1 solar mass is what our sun is, and it's about 6,000 degrees, and because it's burning at that temperature, it appears mostly white or yellowish in colour. We have smaller stars such as red dwarfs. They can be half the mass of the sun or even less, and they burn correspondingly slower or less energetically, so they're only about 3,500 degrees on the surface, so they appear red. It's very much like if you've ever seen a blacksmith heating up iron. The iron starts off black, but as it begins to get hotter, it starts to glow red and then goes up through orange to yellow. And eventually, if you could heat it hot enough, it would actually start to glow blue. because if you get to really, really hot temperatures, such as this blue giant at 30,000 degrees, most of the light it's giving off is in the blue part of the spectrum, so it looks very much blue. It's still giving off yellow and red, but it's dominated by the blue. And so the big blue stars that you can see out in the galaxy, and in those spiral arms in particular, must be given off by these very bright stars that are burning at this very high temperature. The other interesting key fact about this is the blue stars live fast and die young, basically. They go through their fuel like there's no tomorrow. A big star like this one shown here may last only 20 million years, which sounds like a long time to you and me. But as I said, we're talking gigayears, billions of years. So millions of years are peanuts to us. And it's also peanuts to the time on life. I mean, it's 65 million years back to the time when the dinosaurs were born. So we could get 2 or 3 of these blue giants to be born, live and die within that time. That's compared to the sun, which its typical life is about 10 billion years. So they last for most of a good half the life of the universe so far. Red dwarfs, on the other hand, they're very meager with their fuel. They burn for years and years, and maybe 100 billion years is the lifetime for a red dwarf. So they're basically immortal as far as we're concerned. They will last much longer than the universe has been in existence. So they will sit around for almost ever. So there's just a quick chart showing you roughly how these timescales compare. So you can see blue giants are just a tiny fraction of the life of other things. So going back to galaxies, if we're seeing quite a lot of blue stars in the outer arms of those, they must be caused by these big blue giant stars. You don't get very many of those born each year, but you get enough of them to give off this very strong blue light. But given this galaxy is probably 10 billion years old or more, those blue stars can't have been there since the beginning, because they only last a few million years. So this tells us that those stars must be being born and being created all the time. And this seems to be a fact of most of the spiral galaxies that we know of. They are forming stars at a fairly continuous rate. For the Milky Way that we live in, it's about 1 star per year is born in the Milky Way somewhere. Stars take a long time to be born, millions of years again, but a blink of the eye to an astronomer. But on average, there's about 1 new star lights up every year within the Milky Way, or maybe 2 or 3, somewhere around that order. So that's spiral galaxies. Not too much else to say. There's lots of other ones. Here's the Whirlpool Galaxy, which is a very famous nearby target for astrophotography. But one other key fact about spiral galaxies is that the stars are all going around in a very orderly manner. They're all going around together, more or less, apart from a few mavericks in the center. They're all going around together as a sort of pack, all revolving in the same direction, all going around at a fairly constant rate. So it's roughly around 250 million years, 250 million years to go once around the Milky Way, from where the sun is now to the next time we'll be here. So last time we were at this point in the galaxy's life, 250 million years ago, life was sort of wondering about coming out of the oceans onto land, that sort of scale. And the next time you might like to ponder what will be happening next time we're at this point in the galaxy, 250 million years from now. Will we have sorted out Brexit? Will we be allowed out of our houses again? All sorts of interesting things that hopefully will be sorted by then. Who knows though? Now, if we go on to the other big class of galaxies, these are the ellipticals. And these are, in contrast to the spiral galaxies, which are very two-dimensional in shape, very much like the CD. These are very three-dimensional. They're much more like footballs or rugby balls. And their stars are not nearly as well organized. They are quite chaotically, they're all going around the center more or less, but they're going around in every which way. So they're not any clear pattern to what's going on with an elliptical. You can't say they're all going around together. They're all just orbiting the centre, but they're going from every which way. So as I said, these are much more three-dimensional objects, much more better imagined as a football or a rugby ball or something like that. It has a depth as well as a width and a height. I said they come in various sizes and shapes. So this is an E5, NGC1. So this one is slightly elliptical, sort of rugby ball shaped, stretched out a little. This is M89, which is an E0, a very spherical one, almost a perfect football in this case, just round and circular, but with the 3 dimensions. And this is as stretched as they get, an E7. And these, this one is probably stretched out by, you can see a fuzzy blob towards the bottom right there, which is probably helping to stretch this one out. You can't get really beyond an E7. If you get to an E8, then they start to fall apart. They don't really have the structural integrity to stay together. Now, if I go back to one of the early slides when I said there was also another category called the lenticular or S0 galaxies, these you can best think of as something like a spiral galaxy which you can't see any spirals in. So they look much like the CD or the DVD or the 2 fried eggs back to back, but you can't see any spiral structure in them, or at least nothing obvious. And they're also very red, so they seem to have exhausted quite a lot of their fuel, and they're not really making stars anymore. Oh, I should have said that about the ellipticals also. If I just flip back to the ellipticals, you can see these are very red structures, very few blue stars, if any, in them, and they're nearly all made of these sort of red dwarf type stars, because they're not making any new stars now. They've given up that. They're sort of retirement homes for stars, often called red and dead because they're not busy making them. So yes, the lenticulars, which are not quite as common as the others, they're another class of galaxy. The S0s, Hubble had them fitting in between the ellipticals and the spirals. Then we have irregular galaxies. Here's an irregular galaxy. You can see it's a bit of a mess. It doesn't look quite such a mess in the optical, but this one has ultraviolet and infrared overlays on it to show exactly what's going on. M82, quite a nearby target. It's also a starburst. You can see there's something chaotic going on in there, and it's making a lot of new stars. I said the Milky Way is making about 1 to 2 new stars a year, something like that. This is maybe up in the hundreds of new stars. It's having a big burst of star formation, making lots of new stars because something has stirred everything up. And this will, if we come back in another gigayear or so, this will have settled down and probably not making any new stars at that point, given it's had a quick burst of things there. Here's another irregular, a dwarf irregular. You often get dwarf galaxies circling the bigger galaxies, and because of the tidal forces, they can get pulled out of shape, and all sorts of other interesting things can happen to them. So they're often not an obvious shape, but this one's a particularly strung out one there. So that's pretty much everything we need to know about the course knowledge of galaxies. You can now all go away and classify galaxies. If anybody's done that with Galaxy Zoo, you'll probably know all about this. And this puts us into a good place to be. You're all expert galaxy people by now. But that's never quite the answer, is it? There's always something more that we find. So this is one of the interesting things I thought, was that we found another class of galaxies, or a subclass of galaxies perhaps, called active galaxies. So this started in the 1940s by an American astronomer called Carl Seyfert. He was studying galaxies and looking at ones like this one. And he noticed something particular about a small collection of galaxies that he'd looked at, that there were much, much brighter centres than anywhere else in the galaxy, even compared to other galaxies. All galaxies tend to be brighter in the centre than they are towards the edge. But for this particular class of galaxy, which eventually became called Seyfert galaxies, they were much brighter in the centre than he would expect from all the other galaxies he looked at. And he found a small collection of these, wrote a paper on it, and they became named after him by other people, not particularly by him, as the Seyfert galaxies. And people found a few different variants of them. So there's also a Seyfert type 1, a Seyfert type 2, and even Seyfert 1.5 types and things like this. So there was some interesting galaxies there, and people started making collections of those. Then as we got much better with our telescopes, we begin to find other classes of things that were kind of interesting. Here's a Hercules group, Hercules A. This is another galaxy with a very bright centre. But as we got better telescopes, which we could look in other regions of the spectrum, and in particular for this one in the radio spectrum, when you can get really big dishes like they have at Jodrell Bank and you can examine what's going on, here we can overlay what's going on in the radio over just what was on in the optical. And this does reveal quite a lot more is going on. You can see these big jets of material coming out of the galaxy. And not only are they coming out of the galaxy, but they must be coming out at a very high speed, because you have the gravity of all those stars that they've got to exceed to escape from the galaxy. About 400 billion stars there, all trying to drag the gas and stuff that it's shooting out into outer space back, but it seems to be getting out with ease. And also, if we look at the width of the galaxy, I said a typical galaxy is maybe 100,000 light years across. So just looking at the galaxy going from, say, this side here to this side there, I hope you can see the cursor, that's 100,000 years for light, the fastest thing we know, to travel that. So these jets must be shooting out into outer space for much longer than that to build up all this material. We look around, we can see other examples. This is another galaxy, Centaurus A, showing again these big lobes of material shot out sideways at very high speeds. This needs a very energetic source to pump stuff out of the galaxy at such high speed to get away from everything else. As we looked deeper into the sky, we found other strange things, and these were thought to be stars to begin with. These are called quasars. They look very, very bright. They seem to be point sources. In this one on the left, you can see it looks almost like a star, but it is in fact a galaxy. The one on the right, we've had some of the quasar sort of blanked off, and you can see the fuzzy galaxy behind it. So these are extremely bright objects. We can see them halfway across the universe because of their inordinate power that they're putting out. So these were a bit of a puzzle for a while, exactly what they were. They turned out to be galaxies yet again. And we even found even brighter ones called blazars, because we're really not very good at naming things in astronomy. We tend to go with the simplest possible thing you can think of. So this is a very bright quasar called a blazar. And to cut a long story short, which could be a whole talk in itself, it was tracked down eventually that these were most probably, almost everybody agrees on this these days, powered by very large black holes at the centre of galaxies. Nearly every galaxy we've looked at in sufficient detail has a very large supermassive black hole at the centre, and this is the sort of thing that has enough energy, gravitational energy, to power these things. So they seem to be powered by these giant black holes. And this does really help us in astronomy, rather than having to remember blazars, quasars, QSOs, Seyfert type 1s, type 2s, type 1.5s, and so on. This lets us actually bring everything together, and this is now represented by this model. So you can see right at the centre with the letters BH, that's the black hole that's powering the whole thing. The big orange thing that looks a little like a donut is a torus of material that's circling the black hole, and you can see within that a very much smaller pink torus of material. That's material that's about to vanish down the black hole, and this is fallen in towards the black hole at very high speeds getting very hot, a lot of friction there, and this is what's generating this power. And all these things that we've seen, quasars, blazars, Seyferts and whatever, you can see they're all sort of labelled here. There's a Seyfert type 2 down here, Seyfert type 1, radio quiet things up here. We have the blazars, the quasars and various other types, and they're all really just variants of the same thing, looking at them from different angles. Whether this thick torus around here, this orange torus, blocks out some of the light or not, depends what we actually see. So we see different aspects from different angles. So that's active galaxies. What else do we know about? Well, these things aren't completely static. I said it takes about 1 billion years for anything interesting to happen. So we do get car crashes, we get collisions between galaxies. Depending where you live, you may or may not get galaxies colliding into each other. But they're difficult to see with any level of interest because they happen so slowly. Here's two galaxies in the very early stages of coming towards each other. You can see there's a sort of bridge of stars connecting the two here, and if we came back in a billion years or so, these two would have completed their collision and made something of a mess probably at that point. But if we look around the night sky, there's so many galaxies. There's about 2 to 3 trillion galaxies in the universe that we know of, or estimate at least. We can find them in all sorts of stages. So here are 2 galaxies in much further along. They've collided much more completely, and we can see a lot of blue stars here. So there's a lot of star formation caused by these things as they collide and crash together, making plenty of new stars, but probably also spelling their doom, as we'll come on to. Now I've just got a collection of interesting oddities just to show that there's lots of things out there that you can look at and explore, depending on what you like to look at. So we're going to start with the biggest galaxy. This is not the biggest galaxy, this is just a galaxy for scale. So this is a spiral galaxy here. If I shrink that down to this small scale here, this is what the largest galaxy looks like. It's a elliptical galaxy because elliptical galaxies in general are much bigger than spiral galaxies, not always this much bigger. And this one has the catchy name of IC 1101, and this is a Hubble picture of the same. This is the Darth Vader galaxy, discovered by a colleague of mine as he was looking through a lot of pictures, and he thought that looks just like Darth Vader's spaceship. So thank you to Simon Dye for that one. And to go with that, we have the Lightsaber galaxy, which is in GC 5866, but taken in infrared, and it shows up much like a lightsaber. So we got the whole of Star Wars covered. This is the furthest galaxy we've ever seen. This is at redshift of 11, or 13.4 billion light years into the distance. The universe is 13.8 billion light years, so this one was probably not too long after the Big Bang. This form maybe 400 million years after the Big Bang, that sort of thing. This is the furthest one seen as yet, at least the last furthest one I've heard of anyway. It may have been overtaken by now, but it's a particularly distant object anyway. This one's a ring galaxy. Not very many of these known, and just as well because not too sure how they're made. Probably through a collision with something that has removed the centre of it, but we're not really sure. This one's called Hoag's object if you're interested. Another type of galaxy is called the BCG, which is not a Roald Dahl type giant. This is the brightest cluster galaxy and tends to be the biggest galaxy within a cluster of galaxies. Many galaxies form in clusters or groups. So a group is maybe 10 or 20 galaxies altogether, and a cluster is more than that, maybe 100 to 1,000 galaxies. We're a little odd in where we live. We only have one close by neighbour, but many galaxies go around in clusters, and indeed a lot of my colleagues study clusters of galaxies. So this is a brightest cluster galaxy. I said we're really bad at naming things, and this is yet another example of where we're bad at naming things. And now, because I just so love the acronym, LERGs, ULERGs and ELERGs. And I really do challenge you to try and drop this into a conversation. Not that you'll be talking with many people over the next week, at least face to face, but if you're in a Zoom chat or something, drop into this that you've seen a LERG or a ULERG or an ELERG. And these are what are called luminous infrared galaxies. So this is a galaxy here that doesn't look particularly out of the ordinary when you look at it in visible light. It looks fairly dull, in fact. But when you look at it in the infrared part of the spectrum, which is the sort of heat signature, they're extremely bright. And so, because, and this is a bit of a theme, bad at naming things, we call them luminous infrared galaxies, because they're extremely luminous in the infrared. And after a while of collecting these, like we collect stamps, we found a collection of LERGs, and then we found some very bright ones. So, of course, we have to come up with a new name, and here we have the ultra-luminous infrared galaxies, because they're much brighter. And once more, we move on to much even brighter things, and here we have the ELERG, the extremely luminous infrared galaxy. So there you are, something to drop into the conversation about you. Do you ELERG? Have you seen an ELERG? That sort of thing. All great fun. And these seem to be because they have a large amount of dust within them. So the dust tends to absorb a lot of the radiation that the stars within the galaxy are giving out and stops it coming out as light. And it absorbs a lot of this radiation, but like anything else, when you absorb a lot of radiation, you start to heat up. So it starts to glow in the infrared. And that's basically what we're seeing here, is a lot of this infrared radiation given off by these galaxies. There's obviously a lot more to it than that, but that's a good starting point for a LERG. And now we come on to a subject that I've been involved in, simulations, because we don't need to be very clever or have extremely good instruments. We can just simulate things. We can just throw it all at a big computer and go home for the weekend and let it chew over the problem. So simulations is where it's at for me. So certainly some of my colleagues go off to exotic places like Hawaii, mountains of Chile, and use big telescopes like this, which I'll come back to at the end of the talk. And that's where they go to collect more data and to look at further and further objects. Others of my colleagues, they go and look at equations all day, and they work through the maths of the problem, and they can work out all sorts of interesting things. And this is particularly the particle theorists that we share our building at Nottingham with. They do this sort of thing all day. And I thought I'd just show up a quick, this was an abstract for a seminar that we could attend as part of particle theory. And it's one of those things that, I've read this several times now, and it still makes no sense whatsoever to me. But this is looking at new models of the universe as far as I can work out. Some of you may well just be able to read this and understand it, but this is what we're sort of bombarded with on a weekly basis. These exotic theories that the particle theorists come up with to explain how the universe and other things evolve. So if you can make something of that, good for you. This is what I use. I use large computers, and the larger the better. This is the high-performance computer at Nottingham University, or it was. This has now been replaced. I haven't got a picture of the new one, but this one contained about 2,500 processors, and you can throw a reasonable model of the universe onto this machine and let it rip, basically. And we use one really simple equation. This is Einstein's, not Einstein at all, sorry. This is Newton's equation of gravity. As you can see, it's fairly simple. There's only 6 things in there. G is a constant, so it never changes. In our simulations, M1 and M2, which are masses, they never change either, so they're always the same. So it's just saying that force is proportional to the distance between two things squared. So that's pretty easy to solve. We can solve that with pencil and paper quite easily. You can do it analytically for two particles, but once you go beyond two particles, you get into the three-body problem and you can't solve it. So you have to approximate it. And typically in our simulations, we use a billion up to even a trillion particles, and nobody wants to sit around doing calculations, pencil and paper like that. And that's why we use supercomputers, and the bigger the better. Now, luckily, we're helped a little with this because this is what the universe is made up of. 68% dark energy, which we really don't understand. I certainly don't understand it, but I'm not far behind most other people in that nobody really understands it. But for simulations, we can largely ignore that. It only affects things on the really biggest scale, so we just sweep that under the carpet. Now, the regular matter, which is this gas 4% and stars and neutrinos, well, they're not regular matter, and heavy elements, that's about 4 and a bit % of the universe. That's the bit we understand, and that's the bit we've studied for the past, well, up to about the year 2000. That's the bit we studied. The dark matter is the more recent discovery, and that outweighs regular matter about 5 to 1. So if you're just looking at stuff out there and trying to simulate it, to a first approximation, if you just follow the dark matter, that's good enough. You don't have to follow the regular matter, because regular matter is tedious to simulate. You have to take a lot more things into account. Dark matter is a dream to simulate with because it's just so simple and easy to work with. And what we try and produce with our big simulations is pictures of the universe. And this is a picture of the universe. This is one actually produced by telescopes. So we're sitting right in the middle and we're looking outwards up. So we're sitting here and we're looking out. Oops. We're looking out, up this way and down that way. This is above the galaxy and below the galaxy. We can't see easily this way because the galaxy is in the way in both ways. And this picture is composed, each dot on this picture is a galaxy. So we're seeing it, the universe on its biggest scale. So up here is a big cluster of galaxies around here. And down here is a big void of galaxies. So galaxies aren't scattered just randomly around. They tend to clump together in groups and clusters and also disappear from places where we call voids. So that's what we try and build on the biggest scales with our biggest models. And I don't know if this is going to come out very well, but here's a video of a model I produced on the high performance computer at Nottingham. It starts off very fuzzy and very gaseous. So this is soon after the Big Bang. We're counting up there in gigayears since the Big Bang. So we're about 2.8 gigayears, 2.9 gigayears. And you can see it sort of comes together very much like a spider's web. By the way, the universe isn't really spinning around like this all the time and gyrating. I just put this in for artistic effect. But you can see these knots of yellow are where big clusters of galaxies are grouping together. And what we're trying to see is if we can get a similar structure to the last picture I showed you, where galaxies appear in clumps and voids and groups and non-groups, that sort of thing. And we can get pretty good results with this actually nowadays. Certainly the dark matter simulations that we produce are almost now indistinguishable, at least in the broad scale, from the universe in the statistical sense, in that the groupings and clumping together of galaxies really do represent the universe as we see it. This is a snapshot of a bit of it. Let's see if we can see here. This is one of those big clusters of galaxies. Lots going on in there, maybe 1,000 galaxies perhaps all around there. Here's a smaller cluster of galaxies. And we're somewhere out here in the backwaters. Only 2 major galaxies in our area, which we are one. So we're nowhere special. We're certainly not where the excitement is. But that's probably good for us. If you were in one of these big clusters, you're all the time getting collisions between galaxies and galaxies consuming other galaxies. So if you're going to live long and prosper, you're probably not going to do as well out in one of those big clusters as you are in somewhere where we are. And this is just a comparison done by some people. The ones in blue are real data taken from real telescopes of the real sky of galaxies clustered around. And the stuff in red is done from various simulations, in this case, the Millennium simulation. And we can see features in the blue, such as this great Sloan wall up here, which is a big wall of galaxies. And we can see a similar structure in the Millennium. It's never going to be exactly the same. That would be too much to hope that we can make a universe exactly the same as ours, but we can get it statistically identical pretty much. As we go down in level, we don't get quite as good fidelity. We don't make quite, and when we try and simulate galaxies, for instance, we don't quite work as well at that level. But there are some results we can get. Here's a very nice simulation done by Joan Volker-Springle, who is one of the geniuses of simulation. And in this case, he's looking at two spiral galaxies colliding together. And the thing to note about this is you can't see any stars in this because it's a simulation. You can show whatever you like. And what he's chosen to show here is the gas within the galaxy. And he's coloured it blue for cold gas and red for hot gas. And you can see there they've collided together, they've drawn apart, and then they're circling and they're going to come back together. But in the meantime, that gas has all been stirred up and we're getting all sorts of things. We're getting many of these big blue stars that had just been born. They're now exploding as supernovas. They're shooting gas out of the galaxy. So there's not a lot of gas now left in. There's also big black holes in there that may turn into quasars, and they will again shoot gas out. There we go. There's another big explosion of gas shooting out. I hope this is coming over okay in the YouTube. But what we're seeing there is what we started off with was two really nice spiral galaxies with lots of good structure, lots of gas within them. And what we've ended up with is a complete mess, which is probably going to be an elliptical galaxy, and there's very little gas left over. Most of it has been blown out into intergalactic space. And what is left is far too hot, really, to form stars. So that is one of the progressions of galaxies, that we can start off with spiral galaxies that can go into these elliptical galaxies. This is another one. This is a simulation done a number of years ago by NASA, and this is just looking at our own neighbourhood. So this is a simulation of the Milky Way and our other nearby galaxies. So there we are, Andromeda and the Milky Way, nearly the same size. Andromeda is probably slightly bigger than ours, and the Triangulum galaxy is quite small compared to both of them. But you can see as time moves on, and we come up to 4 billion years from now, 4 gigayears, we actually get a collision there of the two galaxies. They go crashing into one another and throw out stars. Some of them will be hurled out of the galaxy, never to return. And then we get more collisions and more collisions and more collisions. And what started off as two lovely spiral galaxies with great structure has now ended up something like an elliptical galaxy with a very chaotic structure. Quite a bit bigger because it's now two galaxies. Oh, and the Triangulum galaxy there, that's not got away. It's just, it will get sucked into this melee later on, but before this simulation completes. So when that happens, we'll come up with something new, probably called Milkdromeda or Andy Way or something like that, who knows. But it's a really bad year, 4 billion years from now. So you've got a fair bit of time, but about 4 billion years is also when our sun starts to get extremely hot, and all life on Earth will probably be boiled alive at that point. So 4 billion years from now, mark it in your diary, it's a good time to be somewhere else. Go and pick a different galaxy to be in at that time. Maybe we'll have the technology by then, who knows. Just a little bit on some open questions, some things that we're still studying. There's quite a number of open questions in galaxies that we don't know all the answers to, which is why we've still got things to do. One thing is what makes supermassive black holes. We really don't have a good theory for how these black holes get so big so quickly. We found some very, very large evidence of very, very large black holes towards the very beginning of the universe, and we don't know how they can form that quickly and be so active. So that's one area that we don't really know how that happens. We'll probably need new instruments to investigate that. Another one that is quite taxing for our department is how things change. So there's two types of galaxy broadly. There's the spirals and the ellipticals, and the spirals are very blue, so they form this blue cloud here, and the ellipticals are very red, and they form this red sequence. But the red ellipticals are much heavier. You can see they're the higher mass. They're much heavier than the blue ones. And there aren't very many in between in this what's called the Green Valley. So we're not really sure how a galaxy makes it from the blue cloud to the red sequence. We're fairly sure they go that way. That's the current thinking. But do they get bigger and then turn from blue to red, or do they go from blue to red and then get bigger? That's not something we really know, and that is an active area of research done by a number of people in our department. So that's still something we've got to work on. Quick few notes about what we can expect in the near future. So this is a space probe launched by ESA called Gaia, and this is going to give us some good results for our own galaxy, the Milky Way. This is mapping the Milky Way in very high detail. I said it's very hard to measure distances to stars. Well, we've put all the best technology we know about measuring distance to stars into this satellite, and it's doing the best it can and is mapping the universe, or not the universe, the Milky Way. It's going to map the nearest billion stars, and we will know exactly where they are and how they're moving. And that lets us make movies like this one, where you can see stars moving around. This one was particularly interested in looking at hypervelocity stars. That's stars that are moving through our galaxy at very high speeds, far too fast to stay within the galaxy. So all these stars here are going to go shooting out of the galaxy. These were caught by Gaia because it not only measures the position of stars, but it also measures how fast they're moving. So that's the perfect thing to drop into a computer to model and just take that forward. So that's one of the things. If you go to the ESA website onto the Gaia page, you can find a number of other movies that they've made from all this data. Next big thing in space telescopes, the Hubble Space Telescope is going to come to the end of its life. It was launched in 1990. Here we are, 2020. So it's been up there 30 years. It's had a few service missions, but still it's pretty old technology at this point. And we don't have the space shuttle or anything similar to service it with, so it's going to die. And this is its replacement, the James Webb Space Telescope. This has had a rather tortuous history. It was proposed in about the 1995 period to be launched in about 2006 at a cost of about $500 million at that time. It's still not been launched. We're in 2020. The latest I'd heard was launch about this time next year, 2021, but what with this virus, that will probably be knocked back. And it's had $8.5 billion spent on it so far. So they've tried to cancel it a couple of times, or various people have, but so much money has been poured into it and so many people's scientific life have been spent on it that it's kind of too big to fail at this point. So it will almost certainly go ahead and launch, and it will be a fantastic instrument when it is launched. But there are one or two issues. You can't launch something this big in a nose cone of a rocket. You can only fit something this big in it. So it has to be folded up to be placed inside the nose cone of a rocket. And then once it's into space, it can unfold itself in a sort of origami type way. And it has to go through all these steps autonomously, initiated from the ground, but has to do all these on its own because it's going to a place out in space a long way, even past the moon. So it's really beyond the reach of anything that we have at present to go and service it. So it has to work perfectly the first time. You can see it's almost complete there. The sun shield is out and the mirrors drop into place and it's all ready to go. It's a much bigger mirror than the Hubble. I think the Hubble was a 1.5 meter. I should write this down. And this is, I think, a 6 meter. It's certainly a lot bigger, has a lot more sensitivity, and of course it's a newer technology. We're in 2020. When Hubble was designed in the 1990s, you think how good your smartphone was at that time and how good it is these days. So we can bring a lot more new technology onto the scene. If we're going into radio astronomy, this is the next big thing in radio astronomy, which we can use to examine very distant galaxies. This is a square kilometre array. This is a big collection of telescopes. In radio telescopes, you can either make really, really big dishes, and the Chinese have pushed this to kind of the limit. They've got a 500 metre, half a kilometre radio dish, although it's fixed in the ground, just sort of looking mostly up. Or you can make lots and lots of small dishes and connect them together with sophisticated computing power, and this is what's been done here. So these are going to be spread across the continent of South Africa and Western Australia and connected together with high-speed computers, and they can sort of turn most of South Africa into a big telescope that you can use to probe the distant parts of the universe and get some good shots of that. So this will help us examine that. The next big thing in optical telescopes, there are 2 or 3 big telescopes being manufactured or built at the moment. This is the biggest one. This is the ELT. That's the one over here. This huge monster. These are some of the biggest ones on the planet at the moment. These are the 8 meter class VLTs, or very large telescopes. I said we have a problem naming things. So these are the VLTs. This is the ELT, the extremely large telescope. So these are 8 meter class. This one is a massive 39 meters. So 39 meters is getting on for half a football pitch. Absolutely gigantic, and it's going to be one of the wonders of the world when it's finished. I think it's about up to lost my cursor, somewhere around this level here. They've poured concrete up to about this level, so it's well on its way to construction. Will probably be showing its first light in 2026 or something like that, providing yet again the virus hasn't slowed it down. There are a couple of other telescopes being built, not quite as big. So as I said, this is a 39 meter or close to 40 meters. There's also a 30 meter and one that's somewhere around 26-ish meters, but due to the way it's built, it's a bit difficult to calculate exactly how big it is because it's made of several mirrors sort of stuck together in a slightly not obvious way. So this is it, the ELT, 39.3 meters across. Huge thing, you can see, compared to standard ESA figures. ESO figures down there, or a pickup truck, or articulated lorry there bringing supplies. This is its mirror laid out in panels. It's a segmented mirror, so made of lots of hexagons. You can see all these people here. This isn't the real mirror, this is cardboard, I believe, just to give you a scale for how big it really is. And it's huge by any standard. You've got to think, you've got to keep that mirror perfectly flat to within, say, 1/10 of a wavelength of light all across its surface, so that it focuses it perfectly. So you can't build it rigidly. You have to have active devices to keep it in perfect focus, no matter which part of the sky you're pointing at. So with that brings us to the end. I hope you've managed to stick with me and it's not gone on too long. And happy to take any questions, although I appreciate there will be a slight lag here. But there we go. Just to conclude, galaxies are really big. I mean, stars are really big and far apart, but galaxies are even bigger and much further apart. As I said, there's 2 to 3 trillion galaxies out there, each with 400 billion stars, so there's lots of room for expansion. And nearly every star we've looked at in enough detail in our own Milky Way seems to have planets of some form around it. So there's plenty of room to go. Research continues. I've outlined a couple of issues that we're looking at Nottingham. And the new telescopes I've shown will not only help us be able to see further, but also further back in time. So if we want to see how galaxies form, we can do very well by looking very distant to the very earliest galaxies and see how they're forming and get clues for how they start off. Do they match the models we make in our computers, even at these early stages? And can this help guide us to yet new ideas about how the universe, life and everything has come about? So thank you very much for listening, and well done if you made it this far. Right, I'll just give it a few seconds, and if you've got any questions, happy to take them now. Or if you've got something better to do, that's also good. See a few people in the chat. Somebody, Mark Stewart from Bristol, observing galaxies. Very good. So one from Richard locally. Are new galaxies forming today, or are they only merging from existing galaxies? So I think most galaxies are really formed by now, and so the ones we see are only getting bigger by consuming other things. They do eat other galaxies. Our own Milky Way has consumed some smaller dwarf galaxies in fairly recent time, and is even now eating a small dwarf galaxy. The Sagittarius dwarf galaxy is being consumed. So we're not completely without guilt here. We're also consuming galaxies. Other questions, Mark Stewart, how do globular clusters form in galaxy halos? That's a really good question. I'm not really sure of the answer to that. It's some idea that maybe these are dwarf galaxies that are stripped, and really you're just left with a very tight core of stars in the center, or maybe they're formed in other ways. They don't really look particularly like what we see in other galaxies, so they may well just form in that way, but it's not really something I'm an expert on. Stuart Porteous, is dark matter uniformly distributed in our simulations? Well, no, it isn't, because if it was, nothing would happen. If it was completely uniformly distributed, then every bit of dark matter would be tugged on by every other bit of dark matter equally. So you have to have some field sort of imposed on it, and we take something from the cosmic microwave background. Basically, we take what we know of from that distribution, and we overlay that on our models to start things off, and we let it evolve from that. So that's good for that. A couple of others. Thank you for your thanks, everybody there. Say somebody else. Yes, it's great. Difficult to see galaxies from a light polluted site, but classified a few on Galaxy Zoo. Thank you very much, John Murrell. We do use the results of Galaxy Zoo in our department to help with our research. It's a fabulous source of raw material to work from, because we can set, people sometimes used to get PhDs for sort of not quite, but counting how many spiral galaxies and how many ellipticals. But thanks to citizen science, that's all been done for us now, and we can now take that data and do something interesting with it. So it's been a great help. So many thanks to those people who've taken part in things like Galaxy Zoo. It is much appreciated because we do use it a lot. Joseph Dobson, is there a way of calculating the mass of a galaxy, or is there really no point? Yes, there is several ways of calculating the mass of a galaxy, actually. And in particular, this gives us the clue about dark matter. So there's a couple of ways. One is just by observing the amount of light. So stars on average, I've said there's stars smaller than us, our sun, stars larger than our sun, but on average they're roughly about the size of our sun. So if you take 4 billion stars or 400 billion stars and average them, it's somewhere like a factor of 2 or 3 the size of the sun. So if you work out how much light is coming from a galaxy and say on average that amount of light is produced by 400 billion stars, all approximately the same of the size of the sun, putting out about that amount, then you can wave your hands vaguely and say, well, in that case, it's putting out this amount of light, this must be this many stars, so it must weigh about this much. So that's one way of weighing the galaxy. Another way is by looking at how the stars rotate in it. You can use Kepler's laws or a version of that to work out the mass inside of the orbit of a star. You can also do it with galaxies circling around each other, and this is actually how dark matter was first discovered, by looking at orbiting galaxies around each other. So there is quite a way of doing it. There's even ways of doing it with X-rays as well. So there's lots of ways of weighing galaxies. They're not particularly precise. You're not going to get them down to the nearest gram or kilogram or even solar mass, but you can get a good order of magnitude, and you can do it, say, 2 or 3 different ways. And if they're broadly in agreement, then you can get a certain amount of confidence with it. Another thanks, Samantha. Would star collision be common in elliptical lenticular galaxies? Not particularly common. The issue is that stars are really, really far apart. I often like to throw in an analogy here. If you shrunk our sun down to the size of a marble, so see that, about half an inch across or something like that, centimetre across, and scaled everything down from that. So where I am sitting in Nottingham, the next nearest star to us on that scale would be in Dover or somewhere like that. So that would be 1 marble in Dover, 1 marble in Nottingham, and they're moving about, and the chances of another marble coming in between those, of actually hitting either of those, is incredibly tiny. So it's very unlikely that 2 stars would collide. Similarly, when the Andromeda Galaxy collides with the Milky Way, there's very unlikely that any 2 stars will collide in that. They will mostly pass through each other. There'll be a lot of disruption, though, by the gravity pulling everything out of its orbits and all that sort of stuff, but there won't probably be any big Hollywood-type smashes. Roy Gresson, what does it mean to say the furthest galaxy is 13.4 billion light years away in a universe that is rapidly expanding? Oh, that's a good one. So we've measured it at 13.4 light years. So that's basically how our measurements are done. But that's the time that the light set off from that galaxy. By now, that galaxy has moved a long way away from where it was, so it's much further away. So it's like 40 billion light years away at this point. But the light we are seeing is from when it first set off, and at that point it was 13.4 billion light years away. So yeah, it's one of those things that you have to get your head a little bit around, and it does take a bit of thinking about. Brendan, why do central bars exist in some galaxies? Oh, that's a good question. I don't think anybody really knows solidly why they appear. They do seem to appear in quite a lot of galaxies. There's been quite a lot of work done on this. In simulations, they often appear just out of nowhere sometimes. We run the simulation, they just seem to pop out, and nobody's quite sure why. So yeah, I'm certainly not an expert on that area, so I'm probably going to duck most of that one and say I'm not too sure why central bars exist, but they do seem quite prominent in quite a lot of galaxies and in our simulations. And it's one of those things that I'm not terribly sure about, so I'm going to duck that one. Thank you for the tricky question, though, Brendan. Right, I think it's probably coming to an end now. A quick one there from Norman James. Why do we know so little about dark matter, and how will we find out more about it? Well, it's not for want of trying. We've detected it by gravity in a number of ways, by rotation patterns in galaxies, by gravitational lensing, by cosmic microwave background, all sorts of. There's about 7 or 8 different strands of evidence that seem to show that it's around. But we really tried hard to detect it through detectors which are going looking for particles that we think might make it up. The trouble is we're not even sure what sort of particle it would be. That's not because we can't think of any. We can actually think of more particles than we can actually go detecting for. There's I'd say about 20 or 30 potential particles that it could be made up of, all of which are theoretical and not being detected. There are 5 or 6 ongoing experiments looking for direct detection, trying to actually grab hold of dark matter in the lab and do experiments on it. All of them so far unsuccessful. But if our theories are right about what it could be, it's going to be phenomenally difficult to detect at all. So whereas we've had success detecting neutrinos, which are also phenomenally difficult to detect, the biggest detectors on the Earth can detect a handful of neutrinos a day, because neutrinos think nothing of passing through 20 light years of lead without bumping into anything. So we can detect a handful of neutrinos a day in our biggest detectors. In the dark matter detectors, if it's the sort of particle we think we're looking for, we might find a couple of months. It's of that sort of scale. So you have to sit around and wait a long time and get rid of a lot of other things that could be messing up your experiment, such as radioactive decay, cosmic rays, all these sorts of things. So it's not for want of trying, but it's pretty hard. So Claire Spencer, where is space? How big is it? And what is it for? I don't really know what space is for, but there's a lot of it. And it's certainly the biggest thing we know of because it comprises the whole universe. And one from Nottingham Astronomical Society from an online question. Our sun is a second generation star, so wood elements on Earth today have been originally formed from another star part of another galaxy or our Milky Way. Well, it's actually probably what we call a third generation star. So we call them population 1 stars because we're a bit backwards. So population 3 would be the first stars. They would be formed soon after the Big Bang. They would probably be very large and be all over very quickly. Then they would form the population 2 stars, which are mostly hydrogen and helium with just a few of the heavier elements in them. They would burn through their life cycle and produce some heavier elements out of it, and they would give us the population 1 star, which is what our sun is. And that has about 2% of other elements besides hydrogen and helium, what we call metals. So we're probably components of maybe 2 or 3 other suns at least have been part of our star. And some recent findings have found we're actually in a big bubble of a supernova. So a supernova has blown up somewhere not too far away, at least in cosmic scale, within our galaxy, and we are sort of within the cloud of stuff that's output. So some of that was almost certainly incorporated into the sun when it first formed, which was about 5 billion years ago. So it's had a fair time to collect this material before it's formed. So with that, I think that's all the questions. Thank you very much for sticking with it, and thank you all for listening. I hope it was successful. I can't really judge from this side, but it seemed to go smoothly in here. At least the dog didn't come racing in and start barking. So that was all successful. So we're hoping to do some more of these, as Richard said in the introduction. And I think we may have one next month on the first Thursday of the month if we can sort out the technology. So best wishes and stay safe, everybody. And thank you and good night.